All right, this isn't the first session of the day, so everyone's awake, right? We're good? All right, we just had a coffee break, so you should definitely be awake. You showed up here. My name is Danica Fine. I'm a developer advocate at Confluent, and today we're going to talk about building out a streaming data pipeline, but an applied one, right? Kind of a fun one. I'm a developer advocate. I'm not like other DAs. I'm a cool DA. So, thank you. I'm glad there's people to react to that. So I borrowed this from a booth downstairs. I hope they don't miss it. But I like to bring props. I think it's fun. It brightens up the room, right? So, oh man, still more people rolling in. Cool. All right, so I want this to be relatable, okay? I want this to be fun, a little interactive, but save the questions for later. To start things off, how many of you have houseplants? Oh my God, okay. That is a large percentage of you. Okay, we can probably be friends. Follow-up question, how many of you have the very bizarre and very specific goal of having an indoor jungle in your home? Okay, non-zero amount, we can definitely talk afterwards. Okay, so that is wonderful to hear. This is gonna be relevant, you're gonna love it, hopefully. So I have a lot of houseplants. I think at its peak, I had about 4 dozen or so. It's a large number of plants. I love them all dearly. They're great. They're all different. They're sprinkled throughout the house. I've had houseplants for a number of years, but it really kind of accelerated over the last couple years. You know, when you're sitting at home, maybe a little depressed, green things in your space, it feels nice. It's an aesthetic, right? Everyone understands that. But it's a problem, right? Because plants take a lot of work. For those of you who have plants, you know that it's not just showing up and taking care of them. It is seeing what needs to be done with the plants, right? It's checking on them. Do they need to be rotated? Do they need to be fertilized right now? Do I need to water them? Have I overwatered? Have I underwatered? So there's a lot that goes into actually taking care of your plants. So, when my collection grew and I had four dozen or so hanging out, this was fine when I was at home, right? I had a number of a lot of free time throughout the day to go and check on my plants and see what needed to be done. But over the past couple months, especially when I'm trying to leave my house, maybe go into the office, do work, see humans, go to conferences, I don't have all the time in the world now to check on my plants and see what they need, right? And, this was bad. This is an exceptionally dramatic plant. Okay, it's fine. It's totally fine now. But what happened was I forgot to check on the plants in the morning before I went into the office, and I got back 10 hours later, and he might not have made it, right? So I'm just being a bad plant mom. So I needed a way to fix this. Okay. So I needed a way to monitor my plants rather than spending time going around my house and checking on them individually. I wanted a system that would help me do this for me, right? And I know what you're thinking. Of course there's a better way. There are systems out there, pre-made solutions that exist to help you monitor your houseplants. So that is not the right question. All right, we're engineers, right? Okay, we're usually looking for the more interesting way to do something or the more fun way. So I figured I have experience. I'm an engineer. I've built a lot of data pipelines in the past. Maybe I have the skill sets, the willpower, and a little bit of time to make my life easier, to help me monitor my plants, but also in a fun and hopefully more interesting way. I really wanted to build something with a Raspberry Pi. I hadn't done a hardware project in the past, so I figured this was my chance, right? I could finally take the time to build out a hardware solution and also use it to showcase what you could do with Kafka, because I also wanted an excuse to bring Kafka into my house. Really weird thing to do, but it was very rewarding. So let's talk design. Obviously, I wanted something to help me monitor my houseplants, right? And let me know when to water them. I figured that was gonna save me a ton of time. I didn't have to do the rounds, spend, an hour or two each day going around checking on individual plants. So the system I envisioned was pretty simple. I'd have the Raspberry Pi with some soil moisture sensors and place them in a couple of plants, take these readings regularly, and Those readings probably wouldn't be good enough to act on their own. I probably, at this point, needed some metadata, and I like using that word. It's a nice hand-wavy thing. I'm not really sure what this data set was at the beginning, but I knew I needed some additional data to help me make a decision on these readings. So I'd throw these both in Kafka, little black box magic in there, and hopefully spit out an alert of some sort. And at this point, I've mentioned Kafka a couple times, so I want to make sure that we're all on the same page. So what is Kafka? Okay, very simply, it's a distributed event streaming platform. Okay, it's a very short, very concise description, but there's a lot to unpack there. So again, just want to make sure that we're all on the same page here. So let's break this down. So Kafka is a distributed event streaming platform. And you may have noticed over the last couple of years, definitely, that we're undergoing a paradigm shift in how we process data. So we're moving from slower batch-oriented systems to more real-time stream processing systems. So rather than wait seconds, minutes, hours to group data and process over that batch, we're instead acting on the data as it's produced in smaller amounts to produce more actionable updates, smaller incremental updates. And we can do this in real time. So moving to stream processing, as I'm sure many of you, have maybe thought about, you're going to increase the accuracy of your data and your results. Your system's going to be more reactive because you're producing results more frequently. And you can also increase the resiliency of your overall system. So what's cool, is that Kafka is a platform that helps to support this paradigm shift, right? It can serve as a messaging system, a persistent storage layer, and also there's a processing layer involved as well. So Kafka gives it to you. But Kafka is a distributed event streaming platform, right? So in order to use Kafka successfully, you really have to embrace the idea of events. All right, you need to start thinking in events. I know that sounds maybe a little intimidating, but I'm going to preface this by saying that as humans, as users, as programmers, I assure you, you already are thinking in and processing in events. Okay, it's just a very natural way to reason about things. You interact with web pages and submit forms online. You look at application logs, at least I hope you do at some point. We react to notifications on our phones and emails. All of these things are events. Okay, you're already interacting with them in your day-to-day life. All I'm asking is that if you're going to use Kafka, is just be a little more conscious of this fact. It's going to save you a lot of time and heartache down the road. So those are examples of events, but what is an event really? It's a piece of information, ideally the smallest amount with too much excess, that completely describes something that has happened. All right? So what do you need to describe that something has happened? You need to know a timestamp. You need to know when that thing happened, who or what was involved, the subject, and then any sort of supporting information to fully flesh out that event. All right, so going back to the example with my plant, this is an umbrella plant that I have at home. So consider the context of the plant monitoring system. So yesterday at 2:30 p.m., my umbrella plant had a moisture level of 19%. Okay, so we have that timestamp notion. Yesterday at 2:30, we have the subject of this event, which is this plant right here, and that supporting detail that the moisture level was 19%. That's pretty simple, right? Very straightforward. But there's another really crucial aspect of events that you need to internalize, and that is that events are meant to be immutable. Okay, I'm sorry if you really like object-oriented things, but we got to focus on the immutability here. So this is due to the fact that they've described things that have already happened, okay? It's just an unfortunate fact of life that an event has happened, we can't go back and change it. I do not have a time machine. If any of you do, see me afterwards, but I don't, okay? So going back to this example, if I go ahead and water my plant and raise its moisture level to 70%, that's great. We've recovered from that low moisture reading, but that doesn't negate the fact that yesterday at 2:30 p.m., it had a low moisture reading of 17%, okay? By watering the plant and having that new reading, all I've done is added another event to the stream of immutable events, this timeline. And if I replay that timeline of events, I can get a full picture of, when I basically watered this plant and, sort of the conditions surrounding this plant over time. So Okay, Kafka is a streaming platform, and it's an event streaming platform, so it really facilitates the movement of these events across the system, which is pretty cool, because then you can quickly communicate immutable events throughout your system, and do that in real time and open up the world for real-time stream processing, all right? Which is pretty cool. I think it's cool. But how does it do that? Okay, let's quickly look a little bit into the architecture behind Kafka. So it's a distributed event streaming system. The primary unit of storage in Kafka is called a Kafka topic, and you put data into the Kafka topic using a separate client called a Kafka Producer. Once the data is in Kafka, you consume that data from Kafka using another client called a consumer. We can have as many producers as we want, producing to as many Kafka topics as we want, and we can also have as many consumers as we want, consuming from as many topics as we want. They are completely decoupled. And another aspect of the consumers is that, yeah, they can all go ahead and consume from whatever topics they'd like, but topics are actually broken down into smaller components called partitions. And what this means is that we can have consumers joining a consumer group and sharing the work of processing data from a single Kafka topic. So you have the option to parallelize the processing and reading of data from an underlying Kafka topic. Right? These partitions in a Kafka topic are themselves immutable append-only logs, and this is where the individual events, the messages, are stored in Kafka. And another thing is that Kafka is a distributed system, as I said. So by breaking up the topics into smaller chunks of partitions, we can then store those individual partitions across different machines in the Kafka cluster. Okay? And by doing so, we ensure a little more fault tolerance, and we also open the door to replication of data. All right, so when we add events to a Kafka topic, here we have one with 3 partitions. We look at the key of that topic and use that to determine which partition we're going to put that data into. So imagine a Kafka cluster with 3 machines in it. These nodes are called brokers. They can be VMs, they can be containers, wherever you want to run them, bare metal. So in this case, we have 3 brokers in the cluster, and we have 3 topics with 3 partitions. I know, very contrived example, but just wanted to illustrate how these are actually spread out. So in this case, if one of these brokers were to go down, we at least ensure that we're not losing all of the data, okay? We're using a small chunk of it, but we're going to take it a step further and focus just on one partition here. And I said that by breaking it into separate partitions, we open the door for replication. So the standard number of replication in a Kafka cluster is 3. So for a given partition, we're going to ensure that there are 3 copies of that data somewhere across the cluster. All right, and ideally, they would live on, the copies of that would live on separate nodes across the cluster. So in this case, we have, focusing on partition 0, we have the leader partition on broker 1, and that leader partition is the leader replica is the one that your producer and consumer is going to be interacting with, and then copies of that partition are going to exist on broker 2 and 3. So in this case, if one of these broker nodes go down, we ensure that we have a full copy of that data elsewhere in the cluster, and we can seamlessly transition over and elect a leader. All right. So that's just a small sample of Kafka architecture. If you're interested, definitely check into it more. It's really cool technology. But back to the project at hand, the thing I really want to talk about. All right, so go back to that Scratchpad. Obviously, this is a really high-level idea of what I wanted to do, with not a lot of details fleshed out. The one thing I really knew at this point was I knew I was going to be spending a lot of time building a physical system, right? I'm working with hardware, first project, not really sure at the get-go how it was going to turn out, right? So from the starting point, I knew that since I was investing all that time in the physical components of the system, I wanted to manage as little infrastructure on the software side of thing as possible, okay? So on that note, I opted to use Confluent. So Confluent offers Kafka clusters fully managed in the cloud so that you can spin up a cluster in a couple minutes and then really just not think about it, right? I can hit the ground running with my Kafka-based project very, very quickly. On top of offering Kafka in the cloud, there are a ton of auxiliary tools that help you integrate external sources and sinks, and then also conduct stream processing and manage your schemas. So we're going to be using a lot of these extra tools as well throughout the project. So with all that in mind, diving a little bit deeper into what I was going to do out of this project, the details. Right? So I'm going to start with that metadata, right? That data set that I wasn't really sure what it was going to be. I figured I needed information on each plant to help me actually make sense of the readings that I was going to be capturing on that plant, right? So I'd probably need to know the moisture threshold that a plant was comfortable within, right? And this is pretty similar for most houseplants, but there are some, outside of the range so I had to play around with that and figure out what moisture thresholds my plants were comfortable in. And I'd also throw in some additional information just so that if I wanted to peek into the pipeline at some point and myself as a human consume this information, I just wanted to know what plant am I looking at, if it has a name that I gave it, where it is in the house, some extra details. So I take this data, feed it into Kafka. Next was capturing those soil moisture readings using the Raspberry Pi. I chose a Raspberry Pi. As I said, I wanted to use one. I was selfish in that regard. But also it seemed to be a little more user-friendly than other options that I'd looked into. So for this stage, I'd be writing a couple Python scripts to help me capture the readings and move them into Kafka as well. With both of those data sets in Kafka, then I would be using stream processing to enrich them, to combine those data sets, and make sense of them, act on it, right? And then finally, once I determined which of those readings were outliers, if my plants needed to be watered, I wanted to receive an alert on my phone. So I have the Telegram app, and I found a way to use Kafka Connect to move that data from Kafka to my phone, which is pretty cool. Okay. So with all that sorted out, I could actually start building things. Yeah, I totally figured out the entire roadmap for the project first before touching any hardware. Right. Anyway, so the Raspberry Pi that I have, for those of you who actually do hardware projects, this is absolutely overkill for what I was doing. Supply chain issues. It was the only one I can get my hands on. I also ended up using a breadboard. I didn't know I needed a breadboard. It came for free with my order, so that was lucky. I settled on these I2C capacitive moisture sensors. I can dive into this deeper with anybody if you're really curious. But these particular sensors were pretty good value for how much they cost, pretty high quality, and they were going to last longer than some other ones that I looked into. So purchased those. And for some reason, I decided that it would be really cool to cut and crimp all of my own wires. So yeah, that was fun. So I purchased some JST connectors and ended up using probably a couple meters of wire in the end. It was really fun. Yeah. Anyway, so the last physical component of the system were obviously the not willing participants, but they were involved. So I chose plants in a very, very scientific way. They were all on the same table, and there was an outlet behind that table. So it was really serious. So I chose a handful of these, and yeah, with the plants decided on, with the hardware components decided on, I could actually go ahead and build the system. And I'm going to do hand waving here because this is not a hardware conference, but again, happy to chat later if you're really curious. Suffice to say, after a lot of soldering, crimping, and a couple tears, I ended up with something like this. Do not judge the soldering too much. It's my first time. So here you see two of the sensors that I was using. A note on the sensors. Okay, so I have, like I said, 4 dozen plants. In the end, I had 4 sensors hooked up to my system. This was a hardware limitation and a complete oversight on my part. So we're using I2C sensors, so they need a unique address in order to communicate that to the Raspberry Pi. And this particular sensor could only physically support 4 unique addresses. So for version 1 of the project, we have 4 sensors hooked up. So they're all communicating over I2C. These are all using the same input channel. So I route this through the breadboard, and that's connected to the Raspberry Pi. And yeah, we're just going to move on so you don't look at that too much. Okay, from the software, this is the more exciting part. If you really care about the specific versions of things that I was using, here it is. I ended up using the Confluent Kafka Python library. And as I mentioned, I was going to be using Confluent for my Kafka-based requirements. So I set up a Kafka cluster completely in the cloud. I'm also going to be doing some stream processing, which is going to happen through KsqlDB, again, completely through the web interface. I'll be using Kafka Connect to move data in and out of Kafka, fully managed, meaning that I don't have to set up any infrastructure on my own, and we'll be taking advantage of Schema registry as well. All right. So now we can actually get started dealing with data. And anytime, I try to be good about this, best practices. Anytime I talk to anyone about starting off on a new data-related project, I always tell everybody just take a step back and really think about the data that you're working with. I feel like a lot of people jump into projects without truly knowing what data sets they're actually going to deal with or where it is, who owns them. And you have to strike a balance between, you don't want to focus too much on where I'm getting the data and what it looks like from the beginning, but you also don't want to think about it at all. So a good way to make sure to find that balance, I think, is to take a step back and write a schema, okay? Especially when you are the person creating the data, and you want to ensure that any sort of downstream systems can, use that data properly and that you're adhering to that sort of contract. A schema is a great place to start, okay? And it also helped me reason about the data sets that I was dealing with, figure out the types that I actually wanted to use, and yeah, just made it a little more clear, a little more real in my mind. So I ended up defining two AVRO schemas. We have the Houseplants data set, which is really that metadata data that I was talking about. So this, as I said, was information on the names of that plant, of course, the thresholds of moisture and temperature that it was comfortable within. And then we also have the readings data set. And from the sensors that I actually had, I was capturing moisture and temperature I got for free, so I included that as well in the data set. And both of these schemas have a houseplant ID, which, assigned at random. And this is going to be used later on as part of the key in the Kafka message, and then also be used to join these data sets later on. Yeah, so with those two schemas defined, I can actually start putting data into Kafka. So there are two main ways to get data into Kafka. We have the Producer API and Kafka Connect. And I know I put verses in there. I'm a confrontational person, so I want there to be some aggression, but there really isn't. It's not really a competition. There are very specific use cases where you're going to want to use the Producer API over Kafka Connect and vice versa. So let's take a look at that. With the Producer API, so this is your low-level vanilla option for putting data into Kafka. You pretty much have the ability to write a client in whatever language you want. You'll pretty much want to use the Producer API if you either own the application that's producing the data or you have access to that particular application. So if, for example, I wanted to capture a very specific type of log events from an application and I own it and I want to move that into Kafka, then I can add a couple lines of code to capture that information and produce it into Kafka as that data is being produced, right? The other option is Kafka Connect. And so Producer API, when you own the application that's generating the data, Kafka Connect is great when you don't own that application, or if the data already exists at rest in some other data source, right? In a database, at the end of an API call, wherever. That data is somewhere else, right? But you want to move it into Kafka to keep it native to the ecosystem and do some stream processing. So Kafka Connect, as the name implies, connects external sources and also syncs. So move data into Kafka. It's great because you don't have to actually use any code. It's completely configuration-based. Another great thing is that through Confluent Cloud, there are dozens of fully managed connectors, meaning that you can set them up strictly through the UI without managing any other infrastructure on your own. So what did I end up using in my case? Surprise, just the Producer API. And I know I said that Kafka Connect is great for connecting to other data sources, databases, and the metadata that I had was definitely something that at some point should be in a database. But remember, I only had four plants with metadata that I had to put into Kafka, so I figured, again, make it a little easier on myself. I was just going to write this data directly to Kafka. Later on, maybe V2 of the system, when I have every plant in my house set up, come find me. I will probably have a database at that point. So wrote a couple scripts with the processor, the producer API, to move the data into Kafka. I would serialize it according to the schemas that I set up, and also assigned at this point a plant ID to use as the key of those messages. So I put the metadata into Kafka, and then from the reading side of things, I created another script with a static mapping of plant ID to the sensor addresses, those I2C addresses. And then I could just go loop through and capture the moisture and temperature data at 5-second intervals, serialize that according to the message, and write it into Kafka. All right, the data is in Kafka. Now we just have to process it. It's easy from here, okay? Yeah, there's a couple different ways to process data with Kafka. The OG way is to leverage that producer API along with the consumer API. These are great because they're available in all your favorite languages, but to use them for real-time processing, it gets a little hairy, okay? You have to go through the full process of consuming the data from a Kafka topic, right, using the consumer API, doing any sort of transformations or stateful and aggregations. You have to do that in memory, handling the state yourself. If you want some failover mechanisms or fault tolerance, anything additional, you have to manage that yourself. And that gets pretty difficult when you're dealing with a stateful application, right? And then once you do that, once you transform the data, you have to write it back to Kafka at the end using the producer API. So you have to manage that whole life cycle. That's a lot of work, as it is the lowest level option available to you. But as you can imagine, there could be a little more flexibility in this, depending on what your application needs are. That said, if you're saying you're going to do one of the other two options, so moving down, we've got Kafka Streams. And Kafka Streams is a Java and Scala library that takes the hassle of managing state off of your hands. It is specifically a library for stream processing. All right, so out of the box, you get a lot of stateful transformations, you have filtering, mapping, joining, windowing. There's a whole host of processors available to you. But what's cool is that it manages that whole state for you, okay? And on top of that, because it's built on top of the producer and consumer API, you get a lot of cool things for free, like scalability. Remember I mentioned those consumers can share the work of processing in parallel. So you can spin up a number of Kafka Streams applications, and they're all going to consume different partitions from the input topic and work in parallel. All right, and then if one of those those instances goes down for some reason, it's going to fail over for you, and the state's going to go with it, right? So you get all that for free. But the easiest and probably the most convenient way to transform data from Kafka is using KsqlDB. What's cool about this is that you don't actually have to write any code. It is completely SQL-based syntax. So you see a little bit of that over here with the joining, selecting. You can window your group by. All of those functions are pretty much available here. But it's built on top of Kafka Streams. I don't want you to think that this is like a toy version of it, okay? Under the hood, when you're using KsqlDB, you're spinning up a Kafka Streams application. Okay, it just makes it a lot easier to do that. You don't have to deal with any of the boilerplate code, right? So you can filter, you can join, do most of the things that you can do in Kafka Streams pretty easily. And taking a step further, what's super cool is that, like I said, you can do this within Confluent Cloud in the web interface. So you don't have to even leave the UI to make this happen. So this is what I chose to use just to make my life easier. Okay. So when we're processing with KsqlDB, there are two main constructs that you have to pay attention to. There are tables and streams. So streams represent unbounded, ongoing events. Okay? Pretty simple, makes sense. Tables, from the context of KsqlD, they represent the current state of the streaming application for a given key. All right. I ended up using both tables and streams in this solution. So first off, let's create a table. So for my Houseplant metadata topic, I chose to use a table, and that's because if I ever wanted to update a value for that metadata for a given plant ID, I want my processing application to reflect that immediately, right? And the table shows the latest value for a given key, all right? So it makes sense that as I'm updating that, I want that to reflect in this table. All right? So we took the time to make an AVRO schema, right? and it pays off here. Okay, so remember, there were like eight or 12, I don't know, there were a lot of fields in that input topic, right, in that schema, but I only have to specify one here, and that's because we have an AVRO schema, and that schema is stored in the schema registry. So as a consumer, KsqlDB has access to the schema registry, can grab that schema, and use that to parse the fields and their types from the underlying topic. So all I have to do here is specify the Kafka topic that I want to pull in to this table. I specify the value format, which is AVRO, and then the only field that I have to specify is the key, the value that I'm going to be using as the key, because it can't decide that for me. So we're just going to use that plant ID as the key that we're using. And once I've written this query, then I can go ahead and go to, this is the Confluent Cloud Console, the KsqlDB Editor. So I have my KsqlDB application, the plant analysis application. And within that, I'm going to execute this create table query, and that's going to materialize that table within my streaming application. Okay. Now let's create a stream. So this is going to be for the readings topic. Even simpler syntax, because I don't have to specify any specific key at all. Again, we're using AVRO, so it's going to parse all of the fields and their types for me. All I have to do is specify the Kafka topic and also the value format. Okay, so I have my table in the application. I have my stream. Both of them are there and accessible and ready to be used as inputs for my stream processing application. The next step, all I have to do is let's enrich the two, right? I need to combine the readings with the metadata to sort of make sense of the readings, all right? And this is going to help me, process later on. So again, SQL syntax. Okay, so we're just going to focus on just this inner select statement here. So it's a stream to table join. I'm just going to do what I would do in SQL, right? An inner join. And I'm using inner join to make sure that we have all of the information that we need to actually do the processing in the next step. So we're joining the Houseplant readings, inner joining that to the metadata, specify the field that we're joining over, and then select all the fields that I want to be as part of that output. Okay. So, great, that is a very familiar syntax, right? But this is a stream processing application. The Houseplant readings topic especially has data coming in on that every couple seconds. So when a new event comes in, we're joining it to the metadata, and we're creating a new output as per this SQL statement. So I want to persist that, right? I want it to be persisted to a stream so I can use it later on. So we're going to take all of those events as they come through and as they're joined, and we're going to output them and persist them to a new stream called the enriched reading stream. We're going to specify the topic that we want that to be backed by, and again, specify that value format. But there's one more crucial component that you have to include in this case, and that's this phrase at the bottom, emit changes. So if I were to just execute that statement, the SQL statement on its own, the select, it would give me a limited subset. It would give me the current state of the application, the data that it is currently aware of. In order to have it process every event as it comes in, I need to specify emit changes. This means that I'm requesting a push query. And this means that I want this result set to be an open-ended stream such that anytime a new event comes in, we're going to do that join and persist it to this topic, every event that comes through, right? And this is contrasted with a pull query. And a pull query is pulling a finite result set that reflects just the current state of the underlying application. So in this case, this is a pretty simple example, but if I just wanted to check into the metadata and see, say, give me the plants whose lowest moisture threshold is above 20%, right? And it's going to spit out a finite result set because, this is the current state of the underlying application. Right? And you can execute this within Confluent Cloud, and this is what you're going to see. All right. So I've enriched the two data sets. I've combined them. They're being persisted to an enriched stream. Now I need to start making sense of the data, right? So let's revisit the overall goal here. Whenever a given plant has enough low moisture readings indicating that it needs to be watered, I want to receive an alert on my phone, right? It's pretty simple. But when do I send an alert, and how often should I be sending them? This is completely a business logic question. What does the end user want? Well, I don't know, I don't want to get, all I knew is that I didn't want to get an alert every 5 seconds if I could help it. So that's how frequently I was taking the readings. So I didn't want to inundate my phone, right? And, if I'm away from my plants, getting an alert every 5 seconds is not going to help me, right? So I figured, getting an alert at most once an hour was probably a reasonable time frame to operate over. It gives me some time to act on water my plant, call my neighbor, tell them to go water the plant or whatever. I also noticed that the sensors weren't perfect, and this happens all the time when you build something at home, right? They were pretty cheap. So sometimes I would get false low or false high readings within a given 10-second interval. It was really frustrating, but the general trend was that the moisture would decrease over time. So I figured, okay, if I'm operating over 1 hour periods, I figured if I receive 20 minutes worth of low readings, that's probably a good enough indication that that plant actually needs to be watered, right? So, so I'm receiving alerts, receiving events every 5 seconds. So over an hour, that's going to be, I would need to get 240 low readings before I send an alert. And this is important. Okay, so given all that information, this is the query that I wrote to make this happen. Okay, so we're going to focus here first on this line here. So I said I wanted to receive alert at most every 1 hour. So we're going to group the data into non-overlapping 1 hour windows. And I can do that with just a couple words, right? Grouping it into 1 hour. And then we're specifically going to count the rows where the moisture from the reading is lower than the low moisture threshold as indicated by the metadata topic. Okay, and we are going to specifically filter that for when the state has 240 low readings, right? So I want to explain this just a little bit more. Okay, remember, this is a stream processing application. It's kind of hard to reason between SQL and an actual stream processing application. So there is state. This is a stateful application. So for a given 1 hour window, per plant, per window, we have a state, and that is within that state we have this low reading count field that we're updating. Okay, so when a row comes in, when an event comes through, if it meets that filter requirement where the moisture is lower than the low moisture threshold, we're going to that state and we're incrementing it, right? So for the first 239 events that come through and meet that threshold, nothing is going to happen. We're simply incrementing that counter within the state. And finally, when that 240th event comes through and meets that criteria and we update that low reading count, that is when a row will be output as part of this query. Okay? So, to summarize, we're only going to receive, per plant, per 1 hour period, we will receive at most one output row from this query, which is exactly what I wanted to get out of it, right? So this query is generating, like I said, at most one row per plant per hour, and we're storing it in a table. It's in a table because this is an aggregation, and it's aggregated per key. And remember, what reflects, the value, the latest value per a key, that is the table. So we're producing it to a table. So the information's in Kafka. I know now when I need to water a plant for a given hour. Okay, now I need to move that information and make it accessible to me. So I have Telegram on my phone, and I wanted to save time. I didn't want to reinvent the wheel here, okay? So I'm going to leverage something that I already have. And from within Telegram, you can set up your own bot. I don't know if anybody's done this. It's crazy. You can do so many cool things now. But you can set up a bot. It takes like 2 minutes to do that. And once you've set up the bot, they give you an API key that you could use to build out a chat interface with it, right? So I had that API key. I started a conversation with this bot on my phone, and from that, I get a unique chat ID between me and that plant bot, my learning bot. So Telegram also has a really cool API so that you can send messages to a specific chat. Who knew? And so I have this endpoint now that Telegram has provided to me, and I can use Kafka Connect, the HTTP sync connector, to push information from Kafka to a given endpoint. right? And it just so happens that this HTTP sync connector is fully managed within Confluent Cloud. So this meant that I just had to walk through a couple quick configurations to set this up and start running it. So to get this connector up and running, so yes, it is drop-down configurable, a couple text fields, but this is the JSON configuration that it spits out at the end, reflecting the underlying connector. So we're just going to point to the Kafka topic that we want to pull the data from to use using those messages as triggers for the sync connector. You see the API URL there, and that contains, I removed it, no one can send things to my bot, has the API key and also my unique chat ID, so we're just going to use the send message endpoint. And then from there, what I'm doing is I'm using regex to capture the specific alert that I want to grab from the underlying Kafka topic. And I'm using that and putting it in the format that the endpoint expects it to be received in. And then from there, this is the alert that I get now. It's kind of adorable. I love it. So now every hour, within a given hour, I can receive an alert from my plants. I use the given name. Most of them have names. It's pretty great. And it tells me, it guilts me into watering them at this point. So it's pretty cool. I enjoy it. Okay, so I know that was fun. Like I said, I love this project. I will definitely build out a lot more hardware-based projects now. But there is a lesson here. Okay, I tricked you. It wasn't just for fun. There's a lesson. This was a real streaming data pipeline, right? And I know it was kind of a toy use case, something that was really applicable to me and maybe, hopefully to some of you. But the individual components from that underlying stream data pipeline are definitely going to be applicable to you if you want to go build out one on your own. So the 3 stages of a stream data pipeline were contained here, and you're going to go through them if you build one out. So you're going to have that initial ingest stage, right? How do I move data from outside in the real world into Kafka? You're going to use the Producer API or Kafka Connect to make that happen. Once the data is in Kafka, you can again go through the transformation stage and enrich the data, do some sort of aggregation if you'd want. And then finally, there's egress. We're going to use maybe Kafka Connect again to move data outside of Kafka to downstream systems, right? So that ingest, transform, and egress is always going to be what you're going to do in a streaming data pipeline. So, and I think I gave you all the tools to figure it out on your own, which is pretty cool. So, if you're looking to play around with it, I love when people bring out their phones and take pictures. It's great. If you're looking to get started, if this is intriguing, so we have our Confluent developer resources over there. This is going to give you pretty much all the tutorials and how-to guides, how to get started with Kafka and Confluent, and get started with cloud-based Kafka if you'd want. And then I also have a link to my repository that contains all of the scripts that I used to capture those readings, as well as the configuration for my connector and all of the queries that I went through to make this project work. So on that note, I can now take questions if anyone has them. Oh, there's a mic coming around.
I'm just wondering, because you've collected so much data, are you going to do any data science on that? Because you could do data science on your plants, but you could do data science on your own behavior in terms of when you're reading messages.
Yes, so there are many more versions of this project coming. I'm just trying to figure out when people are going to be tired of hearing about me talk about plants, right? But yeah, I have so many cool things that I want to do. I just got an intern for the summer, so I'm really excited. But yeah, I was thinking about doing something like that, maybe connecting it with Lambda, and yeah, I've got a lot of cool things that I want to do with it, but yeah, this is just stage 1.
Hi, thanks. First of all, that's pretty cool. Could you elaborate on the window tumbling and data retention part of that query?
Yeah, let's go back. All right. So basically, this is a stateful application, right? And we don't want to retain this information indefinitely. We're just going to exhaust memory, right? So, yeah. It is this easy. There are just two things to specify: the type of window that you want to do. There's tumbling. We have like session windows. There's overlapping ones. But yeah, you just specify the size of that window. You can do minutes, I think, down to honestly like second granularity, up to weeks if you want. But you have to specify a retention because otherwise it can get out of control depending on the volume of data that you're dealing with. So this retention just means that after 7 days, we're going to get rid of this window, this state. I can no longer access it. And for my use case, I don't really need to look back unless I'm doing some crazy, data science at the end to look into my watering habits or lack thereof. It's not really that important for me to keep that beyond a week. So the retention, I think they recently just changed the default, but I just like to use 7 days because I figure I personally don't need it longer than a week, but that's fully configurable.
Right. If I understand correctly, maybe I'm not, but do those 240 low readings all have to be within the same hour? Because then like one accidental high reading might move the last low reading out of the 1 hour window, or not?
Yeah, so great question. This is something that, it came up a couple times, and as I was thinking about the logic behind this. But within that can totally happen. But within the next 1 hour period, if that plant actually needs to be watered, all 240 readings are going to be low in that, or all more than 240 are going to be low within that window anyway. So having that buffer of 1 hour really isn't going to it's not life or death for the plant. So, but yes, you're absolutely right. That could potentially happen. And you could get around that by doing, overlapping windows or having some sort of grace period as well. There's actually a future feature so this is counting up to 240 specifically is kind of a little bit of a hack because there could be, there's a specific case where you could have 2 events come in at the same time and update that. So we could actually have a count equal to 241. I haven't actually seen it happen, but technically it could happen. And then in that case, I'm just relying on the fact that in the next 1 hour window, we're going to capture that. But in a future version of KsqlDB within Confluent Cloud, instead of having emit changes, remember emit changes gives you the intermediate outputs. So instead of using emit changes, I would just use emit final, which means wait till the window closes and then give me a result based on whatever state I've aggregated. So in that case, when I can use emit final, I will just change this to having count over 240. And then it'll wait until that window closes and then give me the result then. So I think that'll come out in the next month or so. So this will be a much simpler query then. And it will avoid those problems that you indicated.
Yeah, I just want to make sure I understand it, because right now, one false reading every 59 minutes could mean that the plant never gets watered, right?
One false reading every 59 minutes. It doesn't have to be 240 readings in a row, right? It's just 240 readings at all within that 1 hour window.
Yeah, but there's only 240 readings per hour.
No, there's 240 readings in a 20-minute period.
Oh, right.
Yeah.
Right.
Yeah,
right.
so.
Yeah. Sorry, that was my mistake then. Yeah, thanks.
Okay, yeah, no problem. Cool. Anyone else?
Thanks. I was just wondering how you decided on the optimal moisture, or what the threshold was for each plant. Is that something that you're going to figure out from your measurements?
A lot of Googling, some testing on the plants. No plants were harmed in the making of this, I promise. But yeah, so basically what I did for a couple of them, there are obviously some houseplants out there that you can just forget about, right? Pothos, snake plant, I hope that means something to anybody. But yeah, you can basically let them, sit there for months and nothing's going to happen. So for those sorts of plants, I basically did a reading after I'd let them sit there forever and found like the lowest threshold for that one. There are some plants that really, really like to be watered a lot more frequently. I think there's like a peperomia. They like to have a higher moisture content. So basically just playing around with it and knowing a lot of my plants, I was able to find a pretty good set of numbers that worked. But I did start off with 25 or 30 as like the low moisture threshold to begin with for all of them. And it went up to, I think, like 70 is usually, 60 or 70 is usually the comfort zone. But then I changed that depending on what I saw in practice. Yep. Cool. One more question.
Let's go first.
Okay, final question, because time is up, so people are going to have to find me afterwards.
Do you have any charts for it? Do you connect it somehow to Grafana or anything to see how it changes?
I have not included any of them here, but yeah, I had a couple that I was playing around with when I was initially looking into like that fact-finding part of seeing what they were comfortable within. But yeah, I can link to those or show you a screenshot later. Yeah.
Thank you.
Cool. All right. Time is up. They're going to kick us out. So yeah, if you have any questions, I do have to return this plant. I think it's Capital One's. So I'll probably be down there, but I'm happy to answer any questions. And yeah, and then I'm also on Twitter if anyone really wants to talk about plants or Raspberry Pi or Kafka. So thank you so much.